Hartung governor. Hartung governor is a type of centrifugal governor used to maintain a constant set speed limit in a steam engine. It is spring-loaded type, right? So we know governors are used to control the speed based on the load, right? There are two types. One is weight control and the other one is spring control. And this type, Hartung governor, is a spring-controlled governor, right? It consists of two bell crank levers pivoted in the frame, right? The frame is attached to the governor spindle shaft and rotates with it. So there are two bolts, and those two bolts are attached to the two bell crank levers pivoted in the frame. So the frame will also rotate with the governor, right? Shaft and rotates with it. Each bell crank lever carries a ball in the vertical arm, right? So the ball is in the vertical arm, and a roller at the horizontal arm, right? So I'll show you the diagram, right? So the roller at the horizontal arm. So since the roller has to move, or sleeve has to move up and down, a roller is attached to the horizontal arm. A coil spring is placed in between the flyball and frame for each bell crank lever. Right? So a spring is attached between the flyballs. Right? So there are two flyballs. So a spring is attached between those flyballs and frame for each bell crank lever. So it is attached to the frame, not to the arm. Okay? Springs provide adequate force to press the rollers against the sleeve. So the responsibility or the duty of the spring is to provide adequate force to press the roller against the sleeve. Right? The speed variation occurs when there are changes in the load driven by the engine. Right? So we know the speed would change if there is a change in the load. Right? So how will it control when the load on the engine increases? Right? So if the load increases, its speed decreases. Hence, the supply of the steam should be increased. Right? So we know if the load increases, automatically the speed of the engine will decrease. Right? So if it is decreased, there's a need to increase the speed. So if there is a need to increase the speed, then the fuel supply should increase, right? So hence the supply of the steam should be increased to reach the set speed limit, right? So we need to increase the steam supply to increase the speed. On the other hand, when the load on the engine decreases, its speed increases. So we know that if the load on the engine decreases, then the speed would increase. So we need to limit the speed, or we need to decrease the speed. In that case, we need to control the supply of the steam, right? So in that case, hence the supply of the steam should be decreased. So we need to decrease the supply of the steam so that the speed would also be decreased to reach the set speed limit. The governor automatically controls the supply of working fluid to the engine with the varying load condition and keeps the mean speed within the set limits. Right? So how does this governor control the supply of the working fluid? By this governor setup, right? So with the varying load conditions and keep the mean speed within the set limits. Right? So if the load increases, the speed will decrease, and the governor has to supply extra fuel to increase the speed. And similar way, if the load decreases, the speed will increase. So governor has to supply extra working fluid. So governor has to reduce the working fluid so that the speed will reduce. Right. So this is how a Hartung governor will function. So here is the setup of the Hartung governor. Right. So there you can see there's a nut, and here is the frame. So this is what called as the frame. Right. This is what called as the frame, and this spring is attached to this frame. Right. This spring is attached to this frame. So what will happen when this governor rotates? Right. When this governor rotates, based on the centrifugal force, right, this sleeve may move up or down depending on the movement of the ball, right? So with the centrifugal force, this ball may tend to move outside if the speed is increased. So if it tends to move outwards due to this bell crank lever, right? If this movement is going their way, this sleeve will move up, right? So in order to accommodate that movement, there is a roller placed here. Right? So this roller will roll so that the sleeve may move upward or downward. Right? So here are the fly balls. So these are the two fly balls, and they are attached to the spring and the frame. Right? And this is the vertical arm. Right? You know, this is the vertical arm, and here is the horizontal arm. Right? And this is the pivot. Okay. So based on this pivot, this bell crank lever may move either this way or this way, right? Horizontal arm and sleeve. So this setup is the sleeve, right? So based on the movement of the balls, this sleeve may move upside or move downside. Okay. Main spindle shaft, right? So this is a main spindle shaft. This frame is attached to this, so this will also rotate along with this shaft. All right. And here is the fly ball, spring, bell crank lever, right? This is our bell crank lever. Okay. And then we have the setup for the engine and the fuel supply. So here, this is the input shaft, bevel gears, right? So the input shaft are connected with the bevel gears. And here is the fuel supply or working fluid supply. Okay. So here's the lever and throttle valve, flow in, flow out. So depending on the motion of this input shaft, the bevel gears will either increase or reduce the speed of the balls, right? So when the angular velocity of the balls increase, the sleeve may either go up or down, right? And due to this movement, this lever, right? This lever will either move this way or this way, controlling this valve, right? So valve body, valve this, so controlling this flow in to flow out, right? So here is a flow in, and this is flow out. This is how it is controlled, right? So this is how the working procedure of this Hartung governor is, right? So you can see it in 3D, right? So this is how the setup would be, right? So this is how this movement will be, right? The vertical arm with fly balls expands by pushing against the spring, right? So depend on the speed, these balls may either move this way or this way, right? So if it is moving this way, the spring expand. If it is moving this way, the spring contract, right? So based on this movement, this roller will either move downwards or upwards, right? Since it's a kind of bell gang lever, right? So this will either move this way or this way. Okay. Up and down movement of the sleeve makes the lever rotate to actuate the valve disc. So depend on this movement, okay, this lever will also move, and based on this movement, this valve will either open or close, right? The horizontal arm pushes the sleeve upwards and pulls the lever, right? The horizontal arm, right? This one is the horizontal arm, pushes the sleeve, right? And pulls the lever. So by this one moving up or down, this lever will also be moving up or down. The lever along with the roller follows the sleeve to actuate the valve disc, right? So based on the movement of this lever, this valve disc will move, right? So there you can see, depending on the motion, this ball may either move that way or this way. Based on that, this spring may either contract or expand, right? So here's a mid position. This is contraction, and this is expansion. This is mid position, and here is the expansion, right? So based on this movement, you can see this sleeve is moving upwards and downwards, right? Based on that movement, you can see this lever is moving this way and this way, and which in turn controls the valve, right? So here are the parts: vertical arm, horizontal arm, sleeve, roller, right? And there are two rollers. One is for the spring, and the other one is for the lever. Okay. So now you can closely observe this motion. All right. So you see the balls move this way, and the spring contracts or expand, and this sleeve moving up or down, which will actuate this lever, which will actuate the flow. Right. So based on that one, this valve will either open or close. Right. So if you can see this movement, arm expands due to centrifugal force produced by the rotating fly balls. Right. So this arm now expands. Arm contracts and come down due to recoil force of the spring. Right. So when the speed reduces, this arm contracts. You see here, right? So depending on the motion, this ball will either come inside or go outside. With high speed, the spring contracts, ball move outside. With low speed, the spring move outside and the ball contracts. Automatic operation of the governor for random speed variation. You see here, based on this flow out is being controlled. Valve closes and opens appropriately based on the speed variation. Right? Hartung governor. So this is also another spring control type governor, as like Hartnell governor. Okay, but here the spring is attached to the frame and the ball. Right? The previous case, Hartnell governor, the spring is attached to the central load, but here the spring is attached to the ball. Right? So a spring governor of the Hartung type is shown in this figure. You can see here. Right? So the spring is attached to the ball or rotating mass. Previously, for the Hartnell governor, the spring is attached to the sleeve or central load. Right? In this type of governor, the vertical arms of the bell crank levers are fitted with spring bolts. Right? So vertical arms of the bell crank lever are fitted with a spring bolt. Right? So this is the vertical arm of the bell crank lever, which is fit with the spring load, which compress against the frame of the governor when the rollers at the horizontal arms press against the sleeve. Right? So when these rollers press against the sleeve, right? So depend on this movement, right? If it press this way, this may tend to move this way. If it press this way, this may tend to press this way, right? Since this is a bell crank lever. Okay. So we'll look at the terms used here. S is the spring force, right? So S is the spring force here or here. FC is centrifugal force, right? FC is the centrifugal force. And M is the mass of the sleeve, right? So M is the mass of the sleeve. X and Y are the lengths of vertical and horizontal arms, right? X vertical arm, Y horizontal arm lengths, right? So the formulation for this one is quite easy, right? So if you can see here, right? This is the mid position, okay? This one is the mid position. So if it is in tilted position, either this may be something like this, or this may be something like this, okay? If you can see here, if it is tilted, I'll try to draw. This may be, if it is pressed against the spring, this may go like this and like this, or it may go like this and this. Okay, so if it is pressed against the spring on this way, when the speed is maximum, this may tend to go like this, or if the spring tend to move this way, right? So from frame to inside, this is from frame to outside. Okay, that's what I mentioned here, right? At minimum speed, this may look like this, right? So here is the mid position. Okay, here is the mid position. So we'll write formulas of moment. Okay, so from this point, this O point, I'll write the formula. Y from O point, we know all the distances. Y we know, X we know, the force FC, force S, mass mg, all are given, right? So FC into X, right, from O, FC, which is acting anti-clockwise, into this distance X, right? So FC is acting in a distance X. FC into X equal S is acting in the clockwise direction, right? S is acting in the clockwise direction. So this X into again X, right? This X, S into again X. So S into X plus mg. Right? So the mg, mass of the sleeve, which is again acting in the clockwise direction, right? Mg. So mg by 2 into, we know the distance, that is y, right? So mg by 2 is acting this way. The distance is y. Okay. So that's all for the solution of this Hartung governor, right? Quite easy compared to the other governors, right? So we just have to take a moment about this fulcrum point O. Centrifugal force Fc and its distance and x is known. Spring forces and its distance x known. Mass of the weight and its distance known, right? So this is how we solve any numerical on Hartung governor. Okay.